So we talked about using the energy of the electron transfer in a galvanic cell, for example, to do work. Well, you may remember that work in chemistry is defined by the Gibbs free energy. And so let's take a look and see how energy fits in with this whole idea of cell potential and work, right? So, depending on the push behind the electrons, in other words, the EMF, E cell, you can either do a lot of work or a little bit of work. If there's not a large value for E cell, then you're not going to do a whole lot of work with this galvanic cell. Now, a volt, which is what we measure E cell in, that's equal to a joule per coulomb. Okay? Q is used in the case of electrochemistry. Q is used to represent the charge in coulombs. Work is in joules, and because the system is producing work, it's doing work on its environment, and work is W is negative. Okay? So the E, the electromotive force, the E cell potential, is equal to negative W over Q. Okay? Work in joules divided by charge in coulombs, which is what volts are. That's how this relationship works. Okay? A Faraday is defined as the number, the charge on 1 mole of electrons, and it's a constant. It's 96,485 coulombs per mole. So charge on electrons is measured in coulombs, and 1 mole of electrons has quite a few coulombs, 96,485. That's Faraday. Okay? So charge is equal to Q, which is equal to the moles of electrons, the number of moles you have, times the Faraday, which is the charge on 1 mole. So the overall charge in your cell, in your system, is going to be equal to the number of moles of electrons transferred times the Faraday. Okay? Work, remember, is equal to delta G. So work then is equal to negative Q times E cell. We just rearranged the previous equation, which is equal to negative N times the Faraday times E cell, which is equal to delta G standard. Okay? So basically what we're saying is that as delta G is negative, E cell will be positive. And that means that the cell is always going to run spontaneously in the direction that gives you a positive E cell or a negative delta G from the last chapter. Okay, so let's do an example. I want to find delta G standard for the following reaction. Copper ions reacting with iron metal to form copper metal and iron 2 ions. Our two half reactions are copper plus 2 electrons goes to copper metal, and iron plus 2 goes to iron 2 plus 2 electrons. So I've already reversed this one for you. Okay, I've already made that the oxidative. When I add them together, I get 0.78 volts. Okay, that's my voltage for this particular cell. Delta G is equal to negative N times F times E. All right, well, what's N? N is the number of moles of electrons transferred. If you look in both half reactions, the number of moles of electrons transferred is 2. So N is 2. Faraday is the Faraday, and E cell is plus 0.78 volts. So 2 moles of electrons, 96,485 coulombs per mole, and 0.78 joules. Our delta G value is negative 1.5 times 10 to the 5th joules. So is this a spontaneous cell? Yes, it is. It will go. Okay, 1.5 times 10 to the 5 joules, or 1,500 kilojoules of delta G. That's a lot of work we can do with this cell. So this makes for a pretty good galvanic cell to produce work. An electrochemical cell that produces a lot of work is called a battery. And that's what a battery is. A battery is nothing more than an electrochemical cell that we harness the electricity to do something. Okay? Here's another example. We have 1 molar nitric acid, and I want to see if that's going to dissolve gold metal to make 1 molar gold-3 solution. Now that doesn't sound like I'm talking about a galvanic cell, but it's still redox, right? Gold of 0 to gold of plus 3, that's oxidation, and NO3 minus to NO2 would be reduction. But whether or not it will happen, we need to see if delta G is negative or E cell is positive. Okay, my half reactions, gold to gold 3 plus 3 electrons, that's the oxidation. That's what we're trying to figure out if it will happen. And since it's an oxidation, that means I must have flipped it. And so I changed the sign of delta E, negative 1.50 volts. The nitric acid reduction has a potential of 0.96 volts, which means our E cell is negative 0.54 volts. Now, right away, I can tell you that if E cell is negative, this is not going to spontaneously happen, right? It's non-spontaneous. So under standard conditions, that means 1 molar solutions, 1 atmosphere of pressure if they're gases, and 298 kelvins, nitric acid will not dissolve gold. You can put gold inside nitric acid, nothing's going to happen. It's not going to oxidize. So if you think back to what we've just done, this is a single displacement reaction. Redox, yes, but single displacement. We've essentially used our reduction potentials instead of looking at the reactivity series. Gold is way at the bottom of the reactivity series. So if you had looked at the reactivity series, you'd say, well, no, gold isn't going to be replaced, isn't going to react with the HNO3 because it's very unreactive. We've just done the same thing, only we've done it with very, very specific numbers. We've shown that the activity series of metals is nothing more than just looking at reduction potential, half reaction reduction potentials. So it's actually kind of a neat little thing. If we had known more about electrochem, we could have done this earlier, but we didn't, so we didn't. So the final thing we're going to do is talk about electrolysis, which is another type of electrochemistry, although the procedure is a little different. Okay, and a galvanic cell, you know, is one where we can produce work. An electrolytic cell is sort of the opposite. We have to put electrical energy in to force a chemical change. So it's kind of the opposite. All right, electrolysis means to break using electricity. Lysis means to break. Electro means electrons or electricity. So what we're going to do is create a cell, and we're going to force a current through it to produce a chemical change that would normally have a negative E cell value. Remember, negative E cell values, they don't want to go. They'd actually, the reverse reaction would go. We're going to put a current into the cell to force it to go backwards. Okay, so we use electrolysis to actually force a reaction that would have a negative E cell. So if you look over here on the left, we have the zinc electrode in zinc ion solution. We have copper electrode in a copper ion solution. The electrons would run from zinc to copper because the voltage is 1.10. Okay. Now, if I want the electrons to go back the other way, in other words, I want to take copper ions and cause them to become copper metal, if I want copper metal to become copper ions and then zinc ions to become zinc metal, in other words, if I wanted to run backwards, I have to add a power source that would have greater than 110 volts because the reverse reaction would have an E cell of negative 1.10. Right? The forward reaction, the one on the left, is positive 1.1, so the reverse is negative 1.1. So if I want it to go backwards, I have to add power that's greater than 1.1 volts. And then I'll get it to go backwards. And then it's an electrolytic. So a galvanic cell goes forward, electrolytic cells go backwards. Now, we can do some calculations using stoichiometry and some things that we know about charge and coulombs and moles and stuff like that. We can figure out what's going to be the result of an electrolytic cell. Okay, we can tell how much of the chemical reaction is going to happen if I know how much current I have and how much time I apply that current. Okay, current is measured in amperes, amps. Okay, and an amp is a coulomb per second. Remember, coulomb is charge. So charge per second, it's kind of like rates. Okay. If we want to electroplate something, electroplating is where we use electricity to deposit a layer of a metal on a different metal. So if you have gold-plated something or other, there's a metal underneath that, and that metal that was underneath that acted as the electrode, and the gold ions plated or reduced themselves to metallic gold on top of that metal. That's what gold plating is. Okay, so reducing the metal ion to create the solid metal on top of another metal, an electrode. That's what gold plating is. The process for figuring out these calculations is pretty simple. Okay, if we know the current that we're applying in the time, okay, we can use the product of current times time, which will give me charge. Use the Faraday, and that'll give me moles of electrons. Use coefficients of the balanced equation, which will give me moles of product, and then use molar mass to get mass or volume of product. Okay, we'll do an example and you'll see how this generally works. All right, so I've got a current of 5 amps and I have a solution of silver ions. I want to plate out silver. I want to reduce the silver to silver metal, and I want to do this so that I'll have 10.5 grams of silver metal. Okay, I want to know how long do I have to put this 5 amp current through my solution to get 10.5 grams of silver to come out of solution. So this is kind of backwards from the diagram that we had before. So we're starting at the bottom and working our way to the top. Okay, there's my half reaction. That's the reaction that I need. For every mole of silver ions, I need a mole of electrons, and I'll produce 1 mole of silver. Okay, so I want 10.5 grams of silver. The first thing I want to know is how many moles of silver is that. So I use the molar mass. Then, according to my balanced half reaction, for every mole of silver metal I want to produce, I need a mole of electrons. So that means that I need 9.73 times 10 to the negative 2 moles of electrons in order for this to work. Okay? Well, if I use the Faraday is coulombs per mole, and if I multiply that by the number of moles, I'll figure out that the total charge I need, and then it's 1 second, 5 coulombs, which is the definition of amperes is coulombs per second, but since I want to figure out how long, what time, I'm going to flip that over. So 5 coulombs per second is 5 amperes, so 1 second over 5 coulombs is just the reciprocal. And then 1 minute for 60 seconds, so I'm going to go into minutes. Okay, so it's going to take 31.3 minutes, a little over half an hour, of running this current through my silver ion solution. I'll have 10.5 grams of silver. Okay, so it's really an easy calculation. The only things that are different from normal stoichiometry is looking at the relationship between moles of electrons and moles of whatever substance you're trying to get out of solution, and then using the Faraday and the current together to get from moles of electrons to time. Okay, and we can go back the other way if you need to. You can start with time and current and go to grams of whatever substance. Okay, pretty straightforward.